Okay, so it's my pleasure to announce the next lecturer, Professor José Seade, who's going to talk about indices of one-forms and invariants of singular varieties.
Okay, so I want to say that I'm really pleased, very happy, and honored to be part of this celebration for César. Many things have been said about him and about IMPA. I just want to add a little thing more, which it's a feeling that I'm sure will be shared by more people, is that for me it has always been a very nice feeling to know that it doesn't matter if I'm really up or down, if I have proved a good result, or if I haven't been able to do anything lately. It's always nice to know that one can come to IMPA, find very nice people, a set of friends, good mathematicians to talk to, a beautiful atmosphere, and that has really, of course César has played an essential role in all of this, and I can say that for me, and for, as Javier also said, for him, and for the group in Dynamical Systems in Mexico, IMPA and César Camacho have played a very, very important role. Thank you. So what I'm going to speak is a joint work, which is a very recent joint work with Wolfgang Ebeling and José Seade, which actually comes from a very, very long list of articles by various people, and some of them are here. I will be mentioning more people along the way, or some of the names are here. And the motivation is to study what should be or what could be a good generalization of the concept of the Miller number when there is not a Miller number. So let me start by recalling briefly what the Miller number is. It's just in a few words. I recall that if we take, let's suppose we have a holomorphic function with 0 in the domain, an isolated critical point. Then we look at f-1 of 0, we call it v, and we can look at also at all the f-1 of t, equals vt for t non-zero. And Miller showed that, so one has a map from Cn plus 1 into C, and he showed that if we take a small puncture disk around the origin, then this map is actually the projection of a locally trivial fiber bundle. There's another way to describe this fibration. I don't want to enter into details. This is the useful way for me. So if we look at all these functions, they actually give you a fiber bundle over a puncture disk. And the topology of the fibers, one of these. So if we look, so we have the singular variety and we have the fibers. We look at one fiber sufficiently, we fix a small ball, sufficiently small, and a sufficiently small, sufficiently near to 0 regular value. We look at the inverse image, and this is the normal fiber. This is the fiber of the Milnor fibration. And then he showed that this has a very simple, with quotation marks, topology. This is, it has, the Milnor fiber always has the homotopy type of a bouquet or a wedge of spheres of middle dimension. So this has complex dimension n, real dimension 2n, and it has the homotopy type of a bouquet of spheres of middle dimension. How many spheres? A certain positive number. This number is the so-called Milnor number. Of course, he didn't call it Milnor number. No? So this is the Milnor number. And he also gave a different interpretation, very useful, very interesting. He showed that mu is the intersection number O of n plus 1 at 0 divided by the Jacobian ideal. So the Milnor number is also this intersection number. So this was for hypersurfaces, and from there, this theorem arised many developments in different areas of mathematics and so on. This concept has been generalized in some directions. For instance, Camacho, Lins, and Seade defined the equivalent number for vector fields. This is the corresponding intersection number. And well, on the other hand, from the viewpoint of singularities, this was published in '68. Soon after that, in the early '70s, Helmut Hamm proved somehow the generalization of this result for complete intersections. So in that case, one has Cn plus k into ck. Instead of one function, one has k functions that define a complete intersection germ. And one looks at the regular value, and Hamm proved that also in that context, the corresponding fiber has the homotopy type of spheres of middle dimension, and then the corresponding number is called the Milnor number of the complete intersection singularity. So the motivation for our work is, what if we will have a singularity which is not a complete intersection? There have been results in this sense previously in the '70s. Groyen and Busch, it's in German, I will just put Busch-Weitz, gave a definition of the Milnor number for curves. And then in the early '80s, Groyen and Steinbrück gave a definition of the Milnor number for normal surface singularities which were smoothable. That means that you have something like a Milnor fiber. And Borenstein, a property which basically it means that there exists a nowhere vanishing holomorphic two-form on a punctual neighborhood of the point. So with those conditions, they gave a definition of the Milnor number. Now, those definitions were aimed to define an invariant which somehow cocked the topology of the Milnor fiber, generalizing these ideas. But in the '70s, late '70s, Pingham showed an example of a two-dimensional surface singularity which had different smoothings whose topology was completely different, and different Taylor characteristic also. So this implies that you cannot define an invariant of a singularity which can be always computed in terms of the topology of the smoothing, because you have different smoothings for the same singularity. So if you want something general, you have to do something else. So this was our motivation. And so the point of view we followed is by using indices of one forms. And that really comes from ideas which Javier, Tatsuro, and other people have been speaking for years about indices of vector fields. So I'm first going to recall briefly these things about indices of vector fields, and then move to one forms. And for that, I'm going to, in the case of hypersurfaces, there are two indices basically, with different interpretations. The first to consider indices of vector fields on singular varieties was Marie-Hélène Schwartz, long ago in '65, for aiming to a different goal. That was directed to constructing chain classes for singular varieties. Then from a different, I'm going to speak a little more, not much more of that in a moment. From a different viewpoint, we defined in the 80s another index which was called GSV index, also was called virtual index, and so on. And I want to recall briefly, because I want to speak about that because somehow we had that index in under the desk, thinking there was no use of it. And precisely in one occasion that our whole group was here at IMPA in a summer, it turned out that that index played a interesting role for us, which actually was not very useful at the end, but it was interesting at the moment. So we started working on that, and that comes from this, something that many of you know maybe better than I. In '82, Camacho and Seade proved this famous separatrix theorem for vector fields. So I'm going to give you this just as a motivation. I'm not really going to into this. So they proved this famous theorem of the separatrices for vector fields in C2. And the natural question by the time was, what about separatrix problem in higher dimensions? Is it true or not? Then somehow, as an intermediate step, later in '88, Camacho showed that there exist surface singularities in C3 with a holomorphic foliation by curves which has no separatrix. So knowing that, somehow a natural idea, a natural approach to constructing counter examples to the separatrix problem would be like this. If one could find a singular variety, with a holomorphic vector field with no separatrices, and if this vector field could be extended to the nearby minor fibers, being tangent to the fibers, and with no more zeros, then you have a vector field in C3 with no separatrices. So the question was, given a holomorphic vector field on this variety, or given a vector field in general, can you extend it to the nearby fibers with no more zeros? So that was the question. And that's what gave rise to this GSV index. And by the way, I would like to mention that that project didn't go very far because not so much later, Mengo and Gomez-Mont gave counterexamples to the separatrix problem, not using indices at all. So this project was not very useful for that, but we started getting into this. So let me define it. Let me recall the definition. So the idea, let me first speak a little about the Schwartz index. I'm going to change a little the position I have there. The Schwartz index and a generalization of it. And this construction is very, in this situation, is very simple. Her context is much more general. She was considering analytic varieties, complex analytic varieties in general, with any type of singular set. So her construction, and she wanted to consider not only one vector, but sets of vector fields. So her context was much more general, much more complicated. In the very, very simple case, when you have an isolated singularity and one vector field, then one can consider a radial vector field. That means it is transversal to every sphere in the ambient space around the singular point. And this works even in the real analytic case, what I'm going to say now. And then you can define a radial index of this vector field to be 1. Why 1? Because 1 is the Euler characteristic of this point, of one point. As I said, her case is much more general, and this is just a very simple case. But now suppose you have a different vector field, which is non-radial. So it has an isolated singularity here. So if you restrict it to this intersection, is called the link. If you restrict it to the link, it's non-zero, but you don't know how it looks. Here you have the radial vector field. So this is a manifold because you are assuming you have an isolated singularity. So you can always put a vector field here in this manifold, which restricts to the radial here and to the given vector field here, and which has isolated singularities. You count how many of these there are. That's independent of the choice of the vector field, depends not only on the radial and the given vector field, and you call it the difference with the radial. So this difference somehow is measuring how far is your vector field from being radial. And then you can define an index of x to be 1 for the radial plus this difference of x with the radial. And you have one generalized, so to say, Schwarz index, or we can call it the radial index of x. So as I said, this was started by Marilyn Schwarz in '65, aiming to construct Schoen classes for singular varieties. This generalization was done more or less at the same time, many years later, in about '96, done independently by King and Trotman, by Suwa and myself, and by Ebeling and José Seade, each one having different applications in mind. So you have this index. And one property of this index, which was the property interesting for Marilyn Schwarz, is that if you happen to have a compact variety with isolated singularities, and you have a global vector field with isolated singularities, then you can count the index here, the local index, like this. And you count, in the smooth part, you count the local index in the usual way, the Poincaré-Hopf. You add it up, and you always get the Euler characteristic of the compact variety. So this index defined in this way somehow gives you the correct number. It gives you the Euler characteristic in the case of the compact variety. The other index I'm going to introduce is different. And in the case of hypersurfaces, the idea of this index is that it is stable under perturbations. And by that I mean perturbations of both the vector field and the variety. Which means that if you move a little, if you move away from the singular variety, you are going to have a vector field here. This is a smooth manifold. You count the Poincaré-Hopf index in this manifold, and that should give you the index in the singular variety. So this index is stable under perturbations. That one is not. But this one gives you the good number, this one gives you something else. So to define it is, I will do it for complete intersections at once. Is here? Well, it's the same thing, sorry. So you have now a variety defined by K equations. Since it is a complete intersections, the gradients, the conjugate are, all of them are orthogonal to the non-singular points. So they are orthogonal to V away from 0, and they are linearly independent because you have a complete intersection. So if you have a vector field, then you have here a set of k plus 1 vectors at each point, linearly independent everywhere. They give you a map from the link into the Stiefel manifold of complex k plus 1 frames in C n plus k. This map was mentioned by, in a more general context, by Suwa in his talk. So this map has a degree, because this manifold is highly connected. All its homotopy groups vanish, except, the first non-zero group is exactly in this dimension. So this map has a degree, and you can define an index of x to be the degree of this map. So this is one example of what Su was mentioned. This can be understood as a residue of the Chern class of a certain virtual bundle, which came later. This interpretation came through the work of Lehmann, Suwa, and Soares. And some properties of this, and some remarks about this indices, that if you extend the vector field to nearby minor fibers, then it's going to have a Poincaré-Hopf index. That Poincaré-Hopf index is the same as the degree I defined before. So this index can be defined as the Poincaré-Hopf index of the vector field on a nearby minor fiber. In the case the vector field is radial, this index is 1 plus minus 1 to the n times the usual minor number of the complete intersection. And, well, I mentioned some things there that we actually define it in our paper. We find it for n more than 1. Somehow we thought n equals 1 was not so interesting, and then Marco Brunella did it for n equals 1, and it seems to be the interesting, very interesting case. And then with Suwa, we just extended the definition for complete intersections. Also, Suwa and Hanedani have in a paper an interpretation for n equals 1. And as I said before, Lehmann, Soares, and Suwa gave an interpretation of this index in terms of residues, using as a residue of a certain Chern class, some virtual bundle. I won't go into that. And now I'm just going to mention this, but I will later go into this because I'm going to use it a lot. Independently, Javier Gómez-Montt kept working from his viewpoint on this, and he defined, I will go into that later, a homological index, which I just leave it now. I will return to this. Well, this homological index, something interesting is that it is something which is very, very important for us, is that it is defined always. The other definitions work only as that setting for local complete intersections. Gómez-Mondt's definition is for a holomorphic vector field on any isolated singularity germ. In the particular case when the germ is a hypersurface, it coincides with the other indices. But it is defined always. And a trivial, so in the case of a complete intersection germ and a vector field, we have two indices, the GSV or virtual index, or in this, if it's a hypersurface, also the homological index, and the radial or Schwarz index. What is the difference? Well, the difference is always with correct sign, the difference is the minor number independently of which vector field you choose. It's always a constant, which is the minor number. So one can take this as the definition, as a definition of the minor number. Now, one difficulty, now if I want to generalize this to the general setting, one problem is that so our first idea was to use the homological index. So because the radial index is defined always, the homological index is defined always, so one can take the difference. And that's well defined, and it's an invariant that is there. Now, what is this invariant, what is this constant, I do not know. For hypersurfaces, it is the usual minimum number. For complete intersections, I suspect it is the minimum number, but it's not known. It's an open problem. So in that case, the question is if the homological index for vector fields is the Poincaré-Hopf index on the minimum fiber for a complete intersection germ. It's not known. So instead of using that, we went round. So before saying how what we did, let me now recall the definition of the homological index of Gomez-Mont. So you start with an isolated singularity in Cn, any singularity, not complete intersection, necessarily anything, and you take a holomorphic vector field. Then you get something like a Cousin complex, which is you consider the n forms in the ambient space. You could consider higher dimensional forms, but he didn't consider them. It's good. So you start in the n dimensions. Now, given any n form and a vector field, you can contract the form, and you get an n minus 1, then n minus 2, and so on, until you get to the functions. So you have this complex, and you can consider the homology of the complex. And you take the Euler characteristic of the complex. I think I forgot the signs. Well, I forgot the, well, here is with signs. I don't know with this. Okay? And you define the index to be the Euler characteristic of this complex. That's the homological index. Now as I said, since for complete intersections we do not know how to handle this number, maybe he knows we didn't. So we decided to go round, and for that we come into ideas which started from a different context by Ebeling and José Seade. So the idea they had is to use one forms instead of vector fields for different, nothing to do with the minimum number initially. So the reason somehow to use forms instead of vector fields is that one, if you have a vector field in the ambient space, the conditions you have to impose on it for being tangent to a manifold or to a singular variety are very strong. So being tangent to a vector field is somehow a very restrictive situation. While if you have a form in the ambient space, you're just restricted to this variety, and you have a form in the variety. And if you want to have it with isolated singularities, all you need to require is that the kernel of the form be in general position with respect to the variety. So it is a very, very general situation. And also, well, forms are somehow can be easier to handle than vector fields. And one interesting reason also for me is that forms are related with codimension 1 holomorphic foliations. So that somehow opens some ideas in that direction. So what to do with forms? So it's very, very much just translating the ideas. So José Seade and Ebeling define, again, for complete intersection germs, that's what they consider, they define two indices. One is the radial, and one is the equivalent of the GSV. To define this radial, the first thing you need to define is, for vector fields, we started, to define the radial index, we started by defining what's a radial vector field. So now you need to say what is a radial form, a radial 1 form, not holomorphic. This is for that definition is for differentiable forms. So what's a radial form? Well, you take some radial vector field. One way to construct this, at each point you have a vector. This gives you a complex line and a basis of that line. So you can look at this tangent space, you have the projection into this line. If you do that at each point, you get a form. That you can call that a radial form. And then you define the index of the radial form to be -1 to the n. Why -1 to the n? Because if this is a smooth point, you want to get the usual index of an isolated singularity of a section of the cotangent bundle of a complex manifold. And that would be it. for a radial index. So for the radial form, you define like this. And then for another form in general, you do exactly, you have exactly the same. You have your one form here, radial. You have your arbitrary differential one form here. You put any one form here, extending the two of them, which is going to have isolated singularities. You count them, that's the difference. And you define the radial index as -1 plus this difference. And you have this radial index for one forms. And also, but here is very interesting. You can do the same trick. You have you have f1 up to fk defining the complete intersection germ. You take the differentials of these functions plus your given form, which is assumed to have an isolated singularity on the singular variety, and all of these give you a k plus 1 frame in the dual complex space. So this again has a degree just in the same way. Now, one nice thing of this situation is the following. For vector fields, one has to consider the vector field and then the gradients conjugate. Why conjugate? Because you want them to be orthogonal to the variety. So you are mixing something, if the vector field is holomorphic, you are mixing a holomorphic with an anti-holomorphic. That makes things more complicated. In this case, everything is, if the form is holomorphic, everything is holomorphic. You can take the map not on K, which is real, but on V minus 0, which is a complex manifold. And then the target is a complex manifold. And then the number you get can be computed as an intersection number in algebraic geometry. That makes things much easier. So they prove this theorem. Well, on the one hand, the index defined in this way is again, you take the one form, is defined in the empty space, you restrict it to a Milnor fiber, you count its zeros with multiplicities, and that equals the index I just defined. On the other hand, if you take the difference of the two indices, this is exactly the Milnor number. And for this index, because of this reason I say that it is intersection number in algebraic geometry, they were able to find an algebraic expression for it, which is actually very, very much very similar to a formula for the computing the Milnor number for an isolated complete intersection, which is a formula proved independently by Le and Groyel. So they have this situation. So now we want to take these ideas and now mimic these ideas to define the homological index. So now, since we don't have a vector field but a form, instead of contracting by the vector field, which is somehow like dividing, well, what do? You multiply by the form. So you have the dual complex. So you start with functions, to go to one forms, and you go up to dimension n. Why dimension n? Because he went to dimension n, so we went to dimension n. Okay? And it's important to remark that this complex exactly was studied long ago by Groyel, and exactly when to give his formula for computing the Milnor number for isolated complete intersection, he considered this complex, just that he didn't consider a one form in general, but the differential of a function. But everything works exactly the same, everything he did. So one has this complex, and one can again look at the homology, and one can look at the, so we know this complex like that, and we can define its homological index like this. I just noticed that we have a shift here in the signs, just because you want to get the correct sign when you're in a smooth manifold. No? And these are the dimensions of the corresponding homology groups. So if we look, let me just return. We notice this is somehow similar to the usual de Rham complex, except that instead of taking exterior derivative of forms, we are multiplying by a fixed one form. And the theorem one has, well, this is actually, this theorem more than a theorem, it's a theorem because I think it's important, but this is essentially a collection of observations. This is really very simple proof based on hard work of others. First is that in the smooth case it is the usual index. Then it satisfies a law of conservation, which is the following. If you let us keep fixed the singular variety, we do not modify the variety, but we perturb the holomorphic form. Then the new forms may have an isolated singularity at the singular point and may have new singularities nearby. You take the usual index in these smooth points plus this one, and that gives you the original index. So that is the law for conservation of the number. And that's proving it can be, I have no idea of how to prove it, except that Gomez-Monta and Giraldo proved a much more general result, which includes this as a particular case. Now, again, something which is a remark, is what is I think interesting, is that if we take forms which are non-singular in the ambient space, and which restrict nicely to the singular variety, those are generic in the singular variety, and they have the minimal possible index in the singular variety. Every other one can be approximated by this type of forms. And so a question I would like to know is, it means that this minimal index is an invariant of the singular variety. Depends only on the singular variety. What it is, I have no idea. And one thing which is essential for those is that in the case of isolated complete intersections, it coincides with the previously defined index. And the reason for that is because of Groyer's work. If we go back to the complex, we have all these homology groups. Then he proved it for the case of when the form was the differential of a function, but the proof works exactly the same in general. He proved that all homology groups are zero, except the top dimensional one. And the top dimensional one equals its dimension equals the number of zeros of the form on the Milnor fiber. So it is the same index. So before continuing, I just make a remark. This also gives an invariant for functions. And if you have a function on the singular variety, a function with an isolated singularity and the singular variety, to this function you can associate its differential and then the homological index of the differential. And that's an invariant for functions on singular varieties. In the particular case when the variety is a complete intersection, this number, this invariant, equals the multiplicity that Isawa and Suwa defined. Again, it's a residue, can be defined in terms of residues of chain classes. And for dimension 1, it also coincides with something which was an invariant introduced by Goryunov and also by David Mond and Dukov and Stratton, which they call the Milnor number for the function on the singular variety. In other words, in simple words, it means that you perturb the function and you look at the number of non-degenerate series of the function, of critical points of the function on a Milnor fiber, and that number is this number. And also, just to mention is, one can also relate this to another invariant of the varieties, which is the local Euler obstruction. I won't go into this because I have no time. Okay, so now again, we have two indices. Given any one form, we have two indices. The difference is independent of the choice of the form. And for complete intersections, that is usual Milnor number. So we can define that as a Milnor number. Okay, so we have this definition of a minor number. And the obvious question is if this is of any interest at all. And as I said, we just finished this work. We still do not have many things to that respect. I think it is interesting. I will give some things now. So we are now working on this project somehow. So the simplest case is obviously when the ambient variety has dimension 1. So then that's the only case we have been able to work in general. So in this case, we have this theorem. So when the variety has dimension 1, it can have many branches. And then it turns out that this minor number defined as the difference of, you have any one form, you take whatever, you take the homological index minus the radial index, kind of two strange invariants you can say, and then you get this very, very nice number. This is the dimension of the space of differential one forms divided by the differentials of functions, so which is somehow, I think, very nice. So our reformulation of this is like this. So we're taking the only characteristic of this complex, the complex of Keller forms with this multiplication. We subtract the Euler characteristic of the same complex but with different arrows, which is given by the exterior derivative. So these are two very nice analytic objects, and then you get this radial index, which is the topological defined. So speaking with people who work in algebraic geometry, they told me that this looks very much like something which I really know less than epsilon, which is about this Simpson's work. The situation here and other people are considering this is what they call a Higgs bundle on a complex manifold. A Higgs bundle means a holomorphic vector bundle with a connection such that the square of the connection is 0. So using this connection, you can look at something like a Dolbeault complex, but where the arrows are multiplication by the connection. So that is somehow this part. Then Simpsons takes that and puts it into a black box using topological arguments, transforms this in some way with topological arguments, and expresses the homology much stronger, not only the other characteristic of the homology, but he expresses the homology of the Higgs bundle with the multiplication given by the connection. That turns out to be equal to the homology of the RAM complex, of the Dolbeault complex, through this topological operation. So this seems to suggest, as they told me, that there could be something like that theory for singular varieties, because that context is for complex manifolds. Here we are in a singular space. So that could be something I would like to explore in the future. And well, I'm going fast because this. So I just have I want to state a few questions. So obvious things to do is to compute our minor number. What kind of invariant is this? For curves we know, in general we do not know. In particular, if you take a resolution of the singularity that has many invariants, one should be able to understand this invariant in terms of the resolution of the singularity. And also the relation with the RAM complex. And taking differential forms in general, we'd like to know. And another thing which I think would be very interesting would be to study the behavior of this invariant under deformations. So the law of conservation of the number of Gomez-Monta and Giraldo tells us that if we keep fixed the complex structure of the variety, and with the form, we have a conservation of the number. But now what happens if we also deform the variety? And that could give, as I mentioned at the beginning of my talk, Pinkham gave examples of a surface singularity with different smoothings whose Euler characteristics are different. An understanding of this could give relationship between if you have different smoothings, what happens among them. Could be interesting. Of course, something which Tatsuo mentioned in his talk is it would be interesting to know if this has a relation with residues. For complete intersection singularities, all these invariants can be expressed as residues of Chern classes in appropriate bundles, of richer bundles. Now, in the case of non-isolated complete intersections, and something which I think would be very interesting is this fifth point, which is, I mean, one forms give you, closed one, one forms give you foliations. Is there a relation with the usual invariance of codimension one foliations, like the Camacho said? So, for example, if we go to surfaces and one-dimensional foliations, which means codimension one foliations, we have the formulas of Brunella and Suwa Hanedani relating the GSV index with the Camacho SAD and with other invariants. So I think it is likely that one can have similar relations for codimension one foliations. And that's all I wanted to say.
So having a smoothing is not enough to have the equality of the cohomological index and the Alcides index?
No. In order to really understand how to answer your question, I would need to know how to compute the homological index in terms of a smoothing. But as I said, Pinkham showed that you have different smoothing with different characteristics. So the smoothing, just like that, is not enough. You have to really make it speak. And I don't know how to make it speak yet.